Dear students, welcome to my channel. Topic of this video is image transform. This is the fourth video on this topic, and in this video I am going to discuss Fourier transform. Now let us start. The Fourier transform is a mathematical tool that analyzes a signal into its spectral components depending on its wavelength. That is, basically it converts the image from time domain or spatial domain to frequency domain. It is used for the variety type of application, for example filtering, removing the unwanted frequency, so we can design low pass filter, high pass filter or band pass filter. Compression, representing the signal more efficiently by discarding the less important frequencies. Communication, efficiently transmitting the signals by focusing on relevant frequencies. Convolving two signals in the time domain is equivalent to multiplying their Fourier transform in the frequency domain and vice versa. This simplifies the calculation and provides a valuable insight into how signals interact with each other. So these are the ways in which we are using the Fourier transform in image processing. Now this is a basic formula, that is two-dimensional discrete Fourier transform. DFT, that is discrete Fourier transform of digitized function f of xy. F of xy is an image, is defined as, now here f of uv, f is nothing but the Fourier domain, that is frequency domain, and u and v are nothing but the rows and columns in the frequency domain, and m and n, x and y are represented in the time domain. Total number of rows are m and total number of columns are n. So this is a formula by which we are separating the frequency component. This formula contains real part and imaginary part. So this is first part is a real part and the second part is imaginary part. So when we apply this formula on image, then we are separating the frequency component from the image. Now actually how the frequency component separated and how it is used. See the one example. F of xy is the input image, we pre-process, after that we take the Fourier transform. So f of xy is converted to f of uv. Then we want to remove a particular frequency from the image, so we use that filter function which will remove the particular frequency. As in f of uv the variety type of frequency gets separated, so based on that we can use this function and we separate or we remove that particular frequency. Then this function is nothing but simply multiplication. After that, as the frequency domain or the transform domain message image is not visible, that's why we are applying the inverse Fourier transform. Now here the every transform is reversible, but when we remove some of the components from the transform, then it becomes the lossy. Then we take the inverse Fourier transform and we do some operation and we are getting the xy or g of xy, that is enhanced image. Now Fourier transform and normalized Fourier transform. For two it is same, that is for example Walsh, Hadamard, they are all same. For f4 they are different. So this is normalized form, this is normalized form and this is unnormalized form. So in this way f2, f4, f8. So here we can use the recursive generation and we can generate the matrix of different sizes. So from f2 we can generate f4, f8. So this we are not going into the detail, but derivation is there, that how we make f4 to f8, f8 to f16. Now we'll see the exercises on one-dimensional signal. To convert one-dimensional signal from time domain to Fourier domain, x of n is equal to f of n into x of n. For simplicity we are using unnormalized transformation matrix. If we are using normalized transformation matrix, at that time in the formula here also 1 by n comes and here also 1 by n comes. So it's all depend on how we are using, but as we are doing calculation manually, so we are using with the unnormalized transformation matrix. X of n is our input signal, f of n is nothing but the Fourier transformation matrix, and x of n, capital X of n, is nothing but our transform signal in frequency domain. As every transform is reversible, we will get back our original signal by applying this function. Now the problem statement. One-dimensional signal is given, that is x of n 1203, and we want to convert this signal, that is spatial domain signal, to the Fourier domain or frequency domain, and again we convert back to our spatial domain, and or we want to show that the Fourier transform is reversible in nature. X of n is equal to f of n into x of n. So this is nothing but f4 matrix of 4 by 4. So we have to remember this matrix, and then as the size of the signal is 4, so f4 is sufficient. So we are multiplying this and we are getting this answer. So this is nothing but the transform signal in Fourier domain. And when we want to take back, then we require to use 1 by n as a normalizing constant. So 1 by 4 into f of n into x of n, and when we do this, we will get again original back our signal. Next similar example is taken 5731. So we take this Fourier matrix of 4 by 4. This is our signal. We multiply, then we are getting the Fourier transform signal. And to reverse that, we are using same. So whatever we are in the previous video, whatever we used for the Walsh-Hadamard and Walsh matrix, the operations are very similar, only there is a change in the transformation matrix. So based on that particular transform, we are using the particular transformation matrix. Here we are using the Fourier transformation matrix. So in the reverse again, we will get the original signal. If we want to do for a signal having the length of 2, then we require, so in this case FW, that is Fourier transform, Walsh transform and Walsh-Hadamard transform are same. So in this way we can apply, and in the reverse we require to just use this factor, that is 1 by 2 into f of n and x of n. We will get again original back the signal. So these problems are similarly solved for Walsh and Walsh-Hadamard transform. You can see this example again. Now we will take back our original signal back by using the above formula. Now we will see the formula for two-dimensional signal. So whatever the formula we used for Walsh and Walsh-Hadamard, they are same, only the transformation matrix is changed. Otherwise rest of the things are same, and for simplification we are using unnormalized transformation matrix, but we can deal with the normalized transformation matrix also. So this two-dimensional signal is given. So this Fourier matrix into two-dimensional signal into again Fourier matrix. So first it will act on the row, and after that it will act on the column. So in this way we require to write down this. First it will act on the row, and after that it will act on the column. So this is nothing but the intermediate result, and we again multiply, we will get this funny matrix. So this is the final Fourier transform domain signal. So this first value is very important because it is nothing but the purely low frequency component from the signal. Similarly, we used 1 by n square f of n into x of n into f of n to get back our original signal. So similar formula is applied, only change in the transformation matrix, and we will get back the original result. Now we will see the another example, that this example is taken. So only we require to take the care that when we are multiplying, we should do the matrix multiplication properly, and even we can't change the order like this. For example, we can't keep f of n into f of n into x of n. So in this way we first find out this matrix multiplication of the first two matrix, and then the resultant is multiplied with this. Again we can convert into our original special domain. Only for two-dimensional we require to do lot of calculation. That's why for simplicity unnormalized transformation matrix is used. Now this is for the two-dimensional signal. The signal is of 2 by 2, so we can use simply this 1 1 1 minus 1, and similarly we can apply the function and we will get again back our original signal. So for 2 by 2 the answers of Walsh, Hadamard and Fourier are same. So again take, so only one problem is taken. Okay, so this is all about the Fourier transform. So in this way we can, using the variety of transformation matrix, and we can convert our time domain or spatial domain signal into another domain, and in another domain we can extract that particular components and do the operation. Thank you.